Okay, hello everyone. In a new video. In this one we are going to solve an exercise related to mechanics in the chapters of energy and linear momentum. This exercise was a previous one in the Terminal LS exams 2021 second session, exercise number 2. The title of this exercise is Studying the Motion of an Object. Then let's start. Consider a rail AOB located in a vertical plane composed of two straight parts, a horizontal part AO and an inclined part OB, making an angle alpha is equal to 30 degrees with the horizontal. So the value of alpha is given by 30 degrees. And we have the two objects S1 and S2 taken as particles of same mass. M is equal to 80 grams, knowing that the SI unit of mass is 0.08 kilograms. Now a massless spring R of force constant K is equal to 200 newtons per meter. Then the moment we have a spring, and regarding energy and linear momentum, we should think about the elastic potential energy. And natural length L0 fixed from one of its ends to a support at A with the other end free. Now take the horizontal plane containing O as the reference level for gravitational potential energy. So this is the P level. So as long as S1 and S2 perform motion along AO, so the potential energy gravitational is neglected, since S1 and S2 passes through the P level. Now G is equal to 10 meters per second square, which means that we are performing this experiment on the surface of the Earth. Now part 1 of this exercise, launching particle S1. Now in order to launch S1, it is placed against the free end of the spring. The spring is compressed by distance d. So what does d represent? D represents the compression of the spring, because initially the free length of the spring is given by L0. Then the moment we compress the spring by distance d, then the spring stores elastic potential energy. And then the system spring S1, so they have mentioned the system that we are working with, which consists of S1 and the spring, is released from rest. So after we compress the spring by the distance d and connect it to S1, it's being released from rest. So release from rest, it means that there is no initial speed. So here there is no initial speed, which means that the kinetic energy is 0. Whereas because the spring is being compressed, it has elastic potential energy. Now let's continue. When the spring returns to its natural length L0, S1 leaves the spring with a velocity v1. So when the spring returns to its initial length, or L0, at this point, it leaves the spring with a velocity given by v1 parallel to AO. After launching S1, moving with the velocity v1 collides head-on with S2, which is placed initially at rest on the rail AO. So S2 is at rest, it has no initial speed. Just after the collision, S1 stops and S2 moves with a velocity v2 parallel to AO, and of magnitude v2 is given by 5 meters per second. So here we can split the problem into two parts. So one before the collision and after the collision. Before the collision, S1 gains speed from the compression of the spring. So here we can notice that this is a problem related to mechanical energy, because S1 gains kinetic energy from the elastic potential energy stored in the spring. So this is the first part of the problem. So this is a conservation of mechanical energy, because we are dealing with a system considered consisting of one mass. After that, S1 will collide with S2. Then in this case, the problem is a conservation of linear momentum. And they are telling us here that S1 and S2 move without friction along the rail AO, in which for this reason the mechanical energy from A to O is conserved. Then we are in part 1.1, and here we know that after collision the speed of S2 is given by v2 is equal to 5 meters per second. Now in 1.1 they are telling us apply the law of conservation of linear momentum to show that the magnitude of v1 is equal to 5 meters per second. So let me write as a title, during collision the linear momentum of the system is conserved, and usually this is statement they give it half a mark, but we need to specify the system. The system that we are working with during collision is given by S1 and S2 is conserved. So in this case, P initial is equal to P final. Now P initial is the sum of the momentums of 1 and N2 before collision. So before collision, S2 was at rest, while S1 was moving with the speed given by V1. So always the momentum carry the same indices of the velocities. So this is P1 plus 0, the 0 vector since S2 was at rest, which is equal to P final correspond to the linear momentum of the system after collision. So after collision, they are telling us that S1 stops, and this is given by the 0 vector, whereas S2 moves with the velocity V2. For this reason, the linear momentum will be P2. Now let's replace the formula of the momentum, which is given by m multiplied by v. Now both particles share the same mass, which is given by m. For this reason, we are going to write mv1, which is equal to mv2. And here, if we refer to the question, they are asking us to calculate the value of v1. Now, what's the type? So we need to determine the magnitude. What's the type of this equation? This is a vectorial equation. Since we want to determine the magnitude, then let's project it. And let me say projection along. So here, the x-axis is already chosen to be along the direction of the inclined plane. Then let me say projection along the direction of the collision. So in this case, we drop down the vector quantities, and each vector quantity will carry a plus or a minus sign. And now, because we want to determine v1, we will not do anything with this one. We will keep it the same, because if v1 now is positive, it will be in the positive direction. Otherwise, it's negative. It means it rebounds back, or it's going in the negative direction. But because we know that S1 is heading toward S2, so we know that the result of v1 will be positive. Otherwise, our calculation is wrong. Now this is equal to what? This is equal to mv2, but they are telling us that S2 moves with the velocity v2 parallel to AO. So here it's obvious that S2 is going to move toward the right, since it's being hit by S1 from the left. So this is equal to plus mv2, and eventually we are searching for the value of v1. So this cancels out of this, because the value of v2 is given by 5 meters per second, then the value of v1 is given by 5 meters per second. So by using the conservation of momentum, we have determined that the speed of S1 before colliding with S is given by 5 meters per second, and this is expected. Why? Since both S1 and S2 have the same masses. Now this 5 meters per second, the speed gained by S1 is actually, which is the kinetic energy, is being gained by the compression of the spring. So now let's proceed. In 1.2, they are asking us to deduce that the collision between S1 and S2 is elastic, and this depends on the value of the kinetic energy of the system initially and final. So kinetic energy initial is given by, so initially only S1 is moving, so the kinetic energy initial of the system is determined by S1, which is given by kinetic energy 1 plus 0, which is equal to half m v1 square, which is equal to half multiplied by 0.08 multiplied by 5 to the power 2. Plugging this on the calculator, then the value of the kinetic energy is given by 1. Says this is in joules, then this is in joules. And finally, kinetic energy final with no surprise. So this is 0 plus kinetic energy 2. This will be equal to half mv2 square, which is equal to half multiplied by 0.085 to the power 2 is equal to 1 joules. Now let me say that since kinetic energy initial is equal to kinetic energy final, then the type of collision is elastic. Let me make some space here. Then in 1.3 they are telling us that determine the value of D. So what does D represent? D represent the compression of the spring when S1 is attached to the spring. And here, because D represents the compression of the spring, one directly should think about the conservation of energy, because D it appears in the formula of the elastic potential energy. And now because we know the speed of S1 when the spring is in its free length, so we know the value of the kinetic energy, which is actually the value of the mechanical energy, and we can apply the principle of conservation of mechanical energy between A and O since there is no friction. And in this case, the elastic potential energy of the spring is completely converted into kinetic. Then in 1.3, let me say, since there is no friction, then the mechanical energy of the system, and here we need to specify the system we are working with, which is given by S1 and the spring. Now we are not going to mention the earth since S1 passes through the PE level along the motion from this point to this point. So let me say that the mechanical energy initial is equal to mechanical energy final. Here we are, these instance initial and final, they are not the same as these because now we have considered another system. Now, so in this case we have that kinetic energy initial plus potential energy initial is equal to kinetic energy final plus potential energy final. And now let's eliminate some of these. Now kinetic energy initial is equal to 0. Why? Because there is no initial speed as being mentioned here, so it is released from rest. We can say released from rest. And so this is 0. Now what about the potential energy final? So when S1 when the spring elongates back to its free length, so it's not compressed anymore, so in this case the potential energy final would be 0, so no compression. So this is 0, and this reflects the fact that all of the potential energy of the spring is being converted into kinetic energy. And we know that let's recall that the formula of the potential energy of the spring is given by half kx squared. So in this case half k, now the compression is not given by x, however by d, so d squared is equal to half m the speed of S1. And notice that the speed of S1 is the speed before colliding with S2, which we have determined here, which is given by v1 to the power 2. And we are interested in determining the value of d. So what's the type of this equation? This is a quadratic in d. Now if we rearrange for d squared, so this is given by m v1 squared divided by k. The value of m is given by 0.08 multiplied by 5 to the power 2 and divided by the value of k. The value of k is given by 200. Now plugging this on the calculator, then the value of d squared is given by 0.01. So in this case we are interested in d. D would be given by the square root of 0.01, which is equal to 0.1. Now everything is expressed in the SI, so the value of d will be in meters because it is a measure of length. Now here notice that I didn't place any unit. You can place a unit, but you need to be careful to place the correct unit, since this is the unit of d square and the unit of d is meter, so this unit will be meter square. Otherwise don't place a unit. Now so we know that the value of d is given by 0.1 meters. Now in number 2 of this question they are telling us motion of S2 on the inclined part OB. So now we reset the clock and we take a new initial instant. So at the instant t0 is equal to 0, S2 starts from O on the inclined plane part OB with a velocity v0 is equal to 5 meters per second. So what does this speed represent? It's the speed of S2 when it reaches the point O, where I is the unit vector along the x-axis parallel to OB. On this part, S2 is submitted to a force of friction of constant magnitude F and of direction opposite to its motion. So let me make some space. Now we are in part 2.1. They are telling us to name the external forces acting on S2 during its motion along the track OB. Notice that they didn't tell us to represent these forces. So when S2 is at this point, for example, between O and B, because it has a mass, it will be subjected to the weight. Because there is a support, it will be subjected to the normal. And because there is a friction opposing the motion, there is friction. So S2 is submitted to three forces given by its weight W, the normal N, and the friction F. Now in number 2.2, show that the sum of the external forces acting on S2 during its upward motion along OB is given by sum of forces is equal to minus F plus mg sine alpha multiplied by the net vector I. And notice that in this case, this is not related to any parameters of motion, whether V or A, which means that this can be calculated independent of Newton's second law. Now let me represent or draw again the figure and represent these forces, because for sure we need to project the forces. So let me say that this is OB. This is X, described by the net vector I. And this is S2. This is the angle alpha, and this is the horizontal. Now let's represent without a scale the forces acting on S2. We have the weight, which is vertically downward. We have the normal, which is perpendicular to the plane. And we have the force of friction, which is acting opposite to the direction of motion along the inclined plane. This is F, this is N, and this is the weight. So sum of forces, here we need to calculate it as a vector quantity. Sum of forces is equal to weight plus the normal plus the friction. And now since we need it as a vector quantity, let's decompose it into the x and the y components. Then wx multiplied by the net vector I plus wy multiplied by the net vector j plus nxi plus nyj plus fxi plus fyj. And here we can directly deduce that. So because n is perpendicular to the x-axis, then this is 0. And because f is parallel to the x-axis, then this is 0. So eventually this is reduced to the following: wxi plus wyj plus nyj plus fxi. W lies along the y and the x, so this is the y. For this reason, we cannot eliminate one of these. Now let me draw the y-axis like this. Now we know that because the motion of S2 only occurs along the x-axis, we can say that wy is equal to minus ny, and the reason is given by no motion along the y-axis. So now if we replace ny by minus wy, so this is wx I plus wyj minus wyj plus fx multiplied by the net vector I, we can notice that these cancel. Now what does wx represent? Wx is the projection of w on the x-axis. So notice that if this is w, then this angle is given by pi by 2 minus alpha. And we know that the projection of a vector, it's either a plus or a minus w, or the magnitude multiplied by the cosine. So notice that w is pointing in the negative direction of the x-axis, so this is minus w cosine pi by 2 minus alpha multiplied by the unit vector I. What about fx? F is completely lying along the x-axis, so here it will be minus f, no need for a cosine because it's parallel to the x-axis. Now w is given by mg. Cosine of pi by minus pi by 2 minus alpha is given by sine alpha multiplied by the unit vector I minus f multiplied by the unit vector I. And here we can notice that if we take minus as a common factor, we have that mg, or we can start by f plus mg sine alpha, and we take on the right the common factor which is given by the unit vector I. So indeed we have proved that sum of forces is equal to minus f plus mg sine alpha multiplied by the unit vector I, and this is reasonable. Vectors exist on the left and vectors exist on the right. Now finally in 2.3 for this exercise they are telling us, and the expression of the linear momentum of S2 during its upward motion along OB is given by that. So knowing that dp by dt is equal to sum of forces, determine the value of f. So we need to use the following equation in order to determine the value of f. So this is a vector equation. F exists in this member. So in order to find f, we need to replace sum of forces by this expression on one side, and on the other side we need to replace dp by dt by another expression, which is this one. So this one can be calculated by applying the derivative. So let me first write that dp by dt is equal to d by dt. Now instead of the p vector I will write it as function of time, which is given by minus 0.9t plus 0.4 multiplied by the unit vector I. So now we need to derive this expression. Notice that I is a unit vector which is constant. It can be dragged out of the derivative. Then we are only deriving minus 0.9t plus 0.4 multiplied by the unit vector I. Because I is a constant, it can be dragged out. Now here we are deriving with respect this expression with respect to time. The linear term becomes constant. So here what do we have? This is equal to minus 0.9. What about the derivative of the constant is 0? So this is simply minus 0.9 I. And here, what is the unit of this quantity? So because this is equal to a force, then this is in Newton. Now we have calculated this on one side, and we know the expression of this, so let's equate them. Here no need to mention any law because already they gave the relation for me, or you can say apply Newton's second law. So because we know that dp by dt is equal to sum of forces, now instead of dp by dt we will place the value which is given by minus 0.9, the unit vector I. Now instead of the sum of forces we are going to write minus f plus mg sine alpha multiplied by the unit vector I. So here, this is, although it's a vector equation, but it consists of two vectors. So first of all, the minus cancels out with the minus, and we can directly say, so this is the magnitude and this is the magnitude, and they are equal to each other. So in this case 0.9, or we can project, which is equal to f plus mg sine alpha, and we are interested in determining the value of f as mentioned in the text. So what's the type of this equation? Linear equation in f. Then f is given by 0.9 minus mg sine alpha. Now 0.9 minus the value of m is given by 0. Let me check. Which is given by 0.08 multiplied by 10 multiplied by sine of 30. And here we need to make sure that the calculator is in the degrees mode. Plugging this on the calculator, then the value of f is given by 0.5. And what's the unit of f is in newtons? Then the value of the force of friction is given by 0.5 in newtons. Then that's it for me in this video, guys. See you soon in a new one.